Hello, welcome to the NPTEL online course on deep learning. You remember in the previous class, we have talked about the linear classifier and the support vector machine. So, what we have done in case of a linear classifier is that we assumed that we have a number of training samples, say training samples yi, which were assumed to belong to class omega I, in the sense that I had a number of training samples from two different classes, the class omega 1 and class omega 2, and using these training samples we wanted to find out a separating plane which separates the samples belonging to class omega 1 and class omega 2. Now, before that, if you remember, when we talked about the discriminant function, for every class we defined a discriminant function which was given by Gix, and in case that the covariance matrix of the training samples coming from all different classes are same, this Gix came out to be a linear one which is of the form W transpose X plus W naught. Of course, if the covariance matrices of the training samples coming from the different classes they are not same, then we have seen that this Gix or the discriminant function of the different classes that does not become linear anymore, but it becomes a quadratic function. So, in case of linear classifier, what we tried to find out is we tried to find out the boundary between two different classes, and when the discriminant functions are linear, then the boundary between two different classes is also linear. Or in the other sense, the boundary between the two different classes is given by Gx is equal to Gix minus Gjx, and if this becomes greater than 0, that means for any given sample x, if the discriminant function for class omega I is greater than the discriminant function for class omega j, in that case Gix minus Gjx becomes greater than 0, and our conclusion is that x belongs to class omega I. Whereas, if Gjx is less than Gix, then obviously x belongs to class omega j. And the boundary between the two classes is given by Gx is equal to 0 when Gix and Gjx are both of them are same. So, in such case, if this Gix or Gjx they are linear as given in this case, then Gx also becomes linear, which is the separating boundary between two different classes. So, given that if you are given a set of samples say belonging to class omega 1 and a set of samples belonging to class omega 2, then the boundary between these two classes omega 1 and omega 2 becomes a linear one. So, when we talked about the linear classifier, we assumed that the boundary is linear. That means, the training samples or the samples belonging to class omega 1 and omega 2 they are linearly separable. And while designing linear classifier, we did not really think of what is the distribution of the vectors belonging to class omega 1 and class omega 2. We simply assumed that they are linearly separable. And we have seen while designing linear classifier is that as over here you find that this straight line is not unique. I can have line over here, I can have a line here, I can have a line here, and so on. So, there are multiple number of solutions possible. And out of this multiple number of separating planes, some of the separating planes gives you lesser margin, some of the separating planes gives you higher margin. So, there we had gone for support vector machines, which ensures that the margin that you get is maximum. That means, your separating plane given say a set of samples to omega 1 and another set of samples to omega 2, it gives you a maximum margin from the samples belonging to class omega 1 and the samples belonging to class omega 2. And this is what was the aim of support vector machine or SVM. So, for all these cases, what we have seen is that you are given a set of training samples for designing the linear classifier or for designing the support vector machine, and those training samples are actually labeled. That means, for each sample I know that from which class or from which category that sample has been taken. Or in other words, every sample or feature vector xi comes with a label yi. So, your samples are given in the form xi, yi. And in case of a linear machine or support vector machine, in case of a linear classifier or a support vector machine that we have discussed so far, because we are concentrating on only two class problem. So, this yi, which actually tells you from which category this sample xi has been taken, this yi can have one of the two values. So, we assumed that yi is plus 1 if xi is taken from class omega 1 and yi is minus 1 if xi is taken from class omega 2. And accordingly, we could have a single classification rule or unified classification rule, which we said that W transpose x plus x W naught of this form. So, this vector x is xi, this whole thing multiplied by yi, that should be greater than 0 if xi is correctly classified by the weight vector W and the margin W naught. This is obvious, because if the sample xi is taken from class omega 1, then my condition is W transpose xi plus W naught should be greater than 0 for correct classification. If it is taken from omega 2, as the sample as omega 2 is on the negative side of the separating plane. So, I have to have W transpose xi plus W naught less than 0, and for samples taken from class omega 2, because yi is minus 1. So, if I multiply this expression W transpose xi plus W naught by yi, which is minus 1 in this case, that will be greater than 0. So, I get a uniform classification rule. So, while designing the support vector machine or while designing the linear classifier, we have taken advantage of this. So, for any xi, when yi W transpose xi plus W naught was less than 0, we had taken that particular W and W naught could not classify xi properly. So, the vectors have to be modified, and that is how we have designed the linear classifier and also the support vector machine. So, in this case also, we assume that we are given a set of feature vectors for training purpose. So, in a multi-class problem, now Wi will not take only two values now, because now we have multiple number of classes. So, what we assume is that suppose I have got n number of feature vectors and I have say k number of categories or k number of classes. So, a training vector which is given in the form x I y I, as I have got n number of feature vectors given for training. So, this I will vary from 1 to n, as there are n number of feature vectors. And my categories, there are k number of categories, and this y I is an index to the category. So, this y I will vary from 1 to k. So, y I is an index to the category. Say for example, if I have 5 categories corresponding to say apple, bird, then cat, dog, car, and so on. If apple is the first category, for apple y I will be equal to 1. If cat is the third category, then for all the vectors belonging to cat class, will have y I value is equal to 3 and so on. So, for example, there is a public database called CIFAR 10. So, this CIFAR 10 database, it contains 50,000 images. So, n is equal to 50,000 and there are 10 categories. So, k is equal to 10 and the categories of images are images belonging to car, images belonging to cat, images belonging to dog, images of sheep, images of horse and so on. So, there are 10 such categories and there are 50,000 images and each of this image is of size 32 by 32 pixels and these are color images. That means, there are 3 planes red, green and blue. So, the number of pixels is 32 by 32 by 3. So, for discussion we will assume that every vector or feature vector given for classification purpose is of dimension d. So, our x I, the feature vectors will be d dimensional and the number of categories k will be and there are k number of categories. So, I have d dimensional feature vectors and I have k number of categories. So, using this, now you find that if I go for the same discriminant function, we had the discriminant function of the form g I x for category omega I or ith category, and this g I x, as we are assuming that our discriminant functions are linear discriminant functions. So, this g I x is nothing but of the form w I transpose x plus w I naught, where this x is a d dimensional vector, w I is also a d dimensional vector. And you find that if I expand this expression, then my g I x becomes of the form w I 1 x 1 plus w I 2 x 2 plus, as there are d number of components. So, I will have w I d x d plus I can write this as w I 0 1, which is the bias term. So, this is what is my g 1 x for category omega 1. Similarly, for category 2, g 2 x will be w sorry, I am taking I is equal to 1. So, this expression will be different. Let me put it like this. So, I want to find out g 1 x, which is nothing but w 1 transpose x plus w 1 naught. As w 1 has got d number of components, x also has got d number of components. So, I can expand this expression in the form w 1 1 x 1 plus w 1 2 x 2 plus w 1 d x d plus w 1 0. This is what is my g 1 x. Similarly, g 2 x becomes w 2 1 x 1 plus w 2 2 x 2 plus continue like this w 2 d x d plus w 2 naught, which is the bias for category 2. And as I have got k number of classes, I will have k number of discriminant functions. So, g k x will be of the form w k 1 x 1 plus w k 2 x 2 w k d x d plus W D W K 0. So, this is your discriminant function G1x, this is the discriminant function G2x, this is the discriminant function Gkx. Now, given this k number of linear equations, you find that I can represent this k number of linear equations in the form of matrix equation. So, the matrix equation simply becomes Wx plus W naught, where this W is a matrix having k number of rows and d number of columns. So, this W is a k by d matrix, and W naught is a bias which is a column vector having d number of components. So, a linear machine is a one which is specified by this matrix W and this bias vector which is W naught. So, they are the parameters of a linear machine. So, once I have this, for given any unknown vector x I, or if I take the training vector x I which belongs to omega I, which belongs to omega I. So, corresponding that my index is y I. So, for this x I y I pair, if I compute this expression W x I plus W 0, this will give me a column vector. Let me call that column vector to be S. So, what this column vector gives? You find that here what you are computing is you are multiplying x I with every row of W. So, if I take the jth row of W to be W j, so this x I is you take the dot product of x I with the jth vector in this matrix W and multiply and add to that the jth component of your bias vector W naught to give the jth component of S or Sj. So, we call this S to be a score function. So, what this linear machine is doing? The linear machine is nothing but a function f which operates on an input vector I. The parameters of the linear machine are say W and W naught, and this gives you a score function which is S, again a d dimensional vector. So, this operation I can say that it is a mapping which mappings map my d dimensional feature vector x d into a score which is of dimension k. And every component of this score vector of this score gives you the score for the corresponding class. So, given my input vector x I, the score component S j tells me that what is the score of this input vector x I to a category omega j as given by the linear machine decided by which are having the parameters W and W naught. So, this is what the linear machine does. And now, if my training vector says that this x I is taken from class omega I or the corresponding class index is y I, then obviously what I would like to see is that for the score function S, the y ith component of this score function should be maximum, so that the classification or the categorization as given by this linear machine is correct. and if it is not correct, then I have to go for correction of the parameters or updation of the parameters of the linear machine, so that the output classification becomes or the error in the categorization or the classification is minimized. So, what I want to do is, I want to now define something called a loss function. So, one thing we have seen is the score function. The linear machine gives you the score function, and the score function indicates that for a given feature vector, what is the score for different classes or for different categories. And I want that this score should be similar to the ground truth. It should be same as the ground truth. That means, if my feature vector belong to class omega 1 or if it is from category 1, in that case, in this score vector that I get, the first component should be maximum and all other components should be less than the first component, so that my classification is correct. If it is not, then I have to go for updation of the parameters of the linear machine, and these parameters are nothing but W and W naught. And by updation, I should be able to tune the parameters so that I get a correct classification. Okay. So, what I want is, before I define this loss function, I want to show this with an example. Say, for example, over here. Here what we are doing is, we have taken an image and this image is flattened out to convert this to a vector. So, how do you flatten it out? You can take every column of the image and concatenate the columns to get a vector, right. So, if I assume that this image is converted to a vector having 4 components, and this is my linear machine, the linear machine takes care of 4 different categories. The categories are cat, bird, dog and car. So, in this case, cat is the first category, bird is the second category, dog is the third category and car is the fourth category. So, for cat, yi will be equal to 1, for bird yi will be taken as 2, for dog it will be taken as 3 and for car it will be taken as 4, which are the indices to all these different categories. So, you find that when you multiply this vector with this matrix W and this is my bias vector W naught, I get this output which is the score. And over here, because this is an image of a bird, you find that the bird score is maximum. If these parameters are not properly tuned, then it is possible that the score for car might be more than the score of bird, in which case my classification that I get, the linear machine, the classification it gives, that is an erroneous classification, and I should be able to modify the parameters or update the parameters. So, in order to do this, what I go for is I define a loss function. Okay, I will come to this a bit later. So, what is a loss function? As I said that if my classification is not correct, or even if my classification is correct, but I want to have better confidence over the classification, or in other words, I want that if the vector xi actually belongs to category omega I or the index is yi, then in the score function syi should be greater than sj for all j not equal to yi. This is what I want, and just that si is more than sj, I may not be satisfied with this, because I want to have more confidence over this classification. So, for that I may like to have syi minus sj should be greater than some delta. So, that is your confidence factor. That means it is not only that Syi should be more than Sj, but Syi should be more than Sj at least by a factor of delta, and only then I will be satisfied, and in such case I will assume that my loss function will be equal to 0. In other cases, I will assume that my loss function will not be 0, but I will have a finite loss function, and that loss value I want to minimize to get the correct classification. I will come to this loss function in details in our previous class, but before that let me just tell you what is the interpretation of this linear machine. So, as we have seen so far that in this linear machine, what we are doing is, for every class or for every category, I have a vector which is a row in the vector W, and for this input vector I am taking the dot product of this input vector with the ith row of my matrix W, the parameter matrix W, and this dot product gives me the score along with the bias term, the score for the ith class of the given vector I. And as you know that when you take the dot product of two different vectors, the dot product gives you a measure of similarity. That is, if the two vectors are similar, then the dot product will be higher. If the two vectors are dissimilar, then the dot product will be lower. So, going by that, I can consider this linear machine, the operation given by a linear machine is something like a template matching operation, or in other words, every row in the parameter vector in the parameter matrix W is a template of that corresponding class, and you are trying to find out, you are trying to match your input vector with that template. And in fact, in CIFAR-10 database, when you train the linear classifiers, you can see that these are the different classes, different categories which the CIFAR-10 database contains. You have the category of plane, car, bird, cat, deer, dog, frog, horse, sheep, and truck. And once the linear machine is properly trained, then all the vectors of your weight matrix W, if you fold it back to form an image, then you will find that those vectors represent the templates of these different categories. Say for example, here this is the template of a plane, this is the template of a car, this is the template of horse, this is the template of truck, and so on. So, these weight vectors that I get for different classes are nothing but these templates, and what the linear machine is doing is it is matching your input vector with these templates. So, I will stop here today. In our next lecture, we will talk about the loss functions, details of the loss functions, and how these loss functions can be used for designing of the linear machine. Thank you.